Last time we did the quantization, or we sketched the quantization of the real Klein-Gordon field, which is a scalar field, and we found the following. So this is going to be the last lecture where I'm giving you this kind of hand-waving overview. From next Tuesday, we'll start going through all the mathematics properly. But just to finish this overview of what quantum field theory is, so we're looking at the real Klein-Gordon field. So it's a real scalar field, fine. At least classically, it's a real scalar field. In the quantum field theory, it's a Hermitian operator field. All right, but we have found that mathematically the system is equivalent to a set of independent simple harmonic oscillators, one for each wave vector k, with Hamiltonian. So for the kth mode, the Hamiltonian is h bar omega a dagger k, a k plus a half, where omega is the square root of mod k squared plus m squared, and we have the commutation relation for these quantities a and a dagger. And I pointed out to you that each mode has energy levels k, like this. So I put in the h bar, nk plus a half, where nk is 0, 1, 2. So we have these energy levels like this, evenly spaced energy levels. So nk is 0, 1, 2, etc. All right, that is the free Klein-Gordon field. Each mode has, of course, the total Hamiltonian. The total Hamiltonian is a sum over the Hamiltonians for the modes. And I pointed out to you that if we have, say, let us say you have a state, we were looking at the following example. Let's say you have the mode K. We're looking at one particular mode. And so we have nk is 0, nk is 1, nk is 2, etc. If you are in the if this mode is excited, if you're in the first energy eigenstate, then you can show that relative to the ground state, the energy, let's call this state psi, then this state is an eigenstate of the Hamiltonian operator with eigenvalue h bar omega, and it's also an eigenstate of the total momentum operator, which we'll define later on. I'll show you how to define the total momentum operator. So this is a vector operator, so it's an operator with three components. And this state is what you normally think of as a particle with energy h bar omega and momentum h bar k. So you might want to label this it's a common notation that you use in this context, is you would just write this as the following state. What does this mean? So there's a notation here. Remember, we have an infinite number of different modes. Okay, there's an infinite number of different modes. And we're looking at we're saying that one mode is excited and all the others are in the ground state. So the K mode is excited. The other modes are in the ground state, which you'll be used to. The ground state of a harmonic oscillator is usually denoted 0. So what is this state? Really, the state, we have a quantum state which is, let's call it capital Psi, which is really a product over all these different states. We've got a ground state, we've got lots of ground states, and then we've got, I assume you know what a tensor product is, a product in Hilbert space. The K mode is excited, okay, and it's just excited in the first state. It has energy h bar omega, momentum h bar k. We'll call that, we'll just write that like this, K. Okay. And then all the other modes are in the ground state. All the other modes are in the ground state. Now conventionally, people get tired of writing, oh, 0, 0, 0. You understood that, okay, I'm talking about, in the context, you say, look, I'm talking about an excited state where there's just one excitation present. You just write this, and I'll put it in quotation marks, but just for ease of writing, you'll just write it as K. Okay, but it's understood that really what this state is a product of an infinite number of states where they're all in the ground state except for one. All right? So the total energy of this state, well, is just the vacuum plus h bar omega plus vacuum for all the other states. And if we take the vacuum state as our zero origin of energy, the extra energy relative to the vacuum is just h bar omega. Okay, so notationally, we will write this. Now, what would happen if we had more than one mode excited? So let's say we had, let's say we have the following. Let's say we had the following. So I'm just sketching. I've got an infinite number of modes. And let's say, so etc., k double prime, they're all in the ground state, except the K mode is in the second excited state. It's in the second excited state. What you find is that, well, So this state here, let's call it psi, this relative to the vacuum, it has energy 2 h bar omega. So it's an eigenstate of the Hamiltonian operator with energy 2 h bar omega. And it's an eigenstate of the total momentum operator with eigenvalue 2 h bar k. Now this is the quantum field theory description of what you would normally call a state when you have two particles of energy h bar omega and h bar k. Alright, I have two particles. Now, note here we're talking about there is one of the field modes is excited. And it has, you might say, well, why can't I just call this one particle of energy 2 h bar omega and 2 h bar k? Fundamentally speaking, all that we have here is a field that has been quantized and has a discrete set of energy levels. This idea of particles, so let's put the word particles in quotation marks. This is heuristic terminology. The key thing here is that you have evenly spaced energy levels. For field modes. And because the energy levels are evenly spaced, it's convenient to think in terms of these excitations. I've got one excitation, I've got two excitations, and people tend to call these particles. But what you will see increasingly, we'll see in quantum field theory, there isn't really, the idea of particles is really just, as I said, a heuristic terminology. I'll talk more about this. Let's also look at the case where I may have had, let's say I've got two different modes excited. So let's say, actually something, let me just go back for a second to that case where I had just one mode with one excitation, this state K. Something you might want to note. So here I'm just going back to the previous example. I had one mode in the first excitation. And I said this is a state with momentum, so with energy h bar omega and momentum h bar k. This state, you can form, of course, superpositions. I could write a state psi that is a superposition, a sum or an integral over k space of different modes. So in each of these terms, one of the modes is excited. I could have a superposition of states where in one term this mode is excited, in the next term the other mode's excited, next term the other mode's excited. So this would be a superposition of states with different momenta. A superposition of what heuristically you would call single particle states with different momenta. And this is the sort of thing that you're used to dealing with within the basic quantum mechanics you studied. So this kind of situation, if you looked at this in the low energy domain, at low energies, so where the energy here is well, the energy here is h bar omega, which is h bar square root of mod k squared plus m squared. If this energy is approximately just, there's a c here, the c is equal to 1. This is stuff that is normally not even mentioned in an introductory course, but in fact it's never, you hardly ever even see it mentioned even in advanced textbooks. But to give you a sense, how do I get back to the ordinary quantum mechanics of a low energy particle? If you look at small wave numbers, where the energy of this system, or of this mode, is just the rest energy plus a small amount, what you find is that a state like this, it behaves like the low energy wave function. So the low energy wave function that you meet in non-relativistic quantum mechanics can be constructed like this. It's something you might want to, those of you who are keen, you might want to look at it over the weekend, but you can see this is actually how it emerges. All right, so let me just say one more thing, is what happens if I have two different modes excited at the same time. Okay, here I have a superposition where in each term there's just one mode excited. So this is a superposition of terms where in each term there's one particle, if you like. What if I have a state that looks like this? I've got your ground state, and I'm in the first excited state, and I'm in the first excited state, and then the ground state, going on and on. So this is the mode K, this is the mode K primed. So I've got two different modes that are in the first excitation. So you find here that, well, what happens, it's called the state psi. What it is, again, an eigenstate of the total Hamiltonian. And the eigenvalue, as you might guess, is h bar omega plus h bar omega prime. And if you look at the total momentum operator, which we'll define later, the eigenvalue is h bar k plus h bar k primed. Now again, it's a field system where now I have two modes excited. These are the values of the energy and the momentum. The heuristic particle interpretation what does it say? It says I have a two-particle state. A two-particle state. So one particle has energy h bar omega and momentum h bar k. The other has energy h bar omega prime and momentum h bar k prime. So I've got two particles present with different energies and different momentum. This is a two-particle state in quantum field theory. Okay. One can go on. I'm going to go on and just tell you about the electromagnetic field now. But before I do that, are there any questions on this? Any questions?
So how could we differ the two particle modes? Like if omega here equal to omega prime, then how could we differ this case with the previous case?
Right. Well, so if omega was equal to omega prime, then so let me see. You're saying if I take the limit in which, I mean, if omega was actually equal to omega prime, then I would have two excitations of the same mode. But I guess it would be an interesting question if you say, if I take the limit as omega approaches omega prime, what would be the difference? So what would be the difference? The difference would be infinitesimal. I mean, I would have, here you would have, you would say that there are two particles, one with energy h bar omega, and the other with energy h bar omega prime, which is almost the same. So I have two particles with almost the same energy. In the case where I had the second mode excited, I would say, well, there are two particles present with exactly the same energy. You know, if you could measure precisely enough, you would see a small difference. But the case is, you know, you become infinitesimally close. I'm not sure, does that answer your question, or maybe not quite anyway. But, any other questions? Questions? All right, okay, so this is, let me now tell you about how this generalizes to the electromagnetic field, which is very simple. We're going to go through the formal quantization, and it's a bit more involved because the electromagnetic field is a vector field, and but the result that you get, let's now look at the electromagnetic field. So this can be written, so what we're going to do, the first start next week, we're going to look in the Coulomb gauge, where the divergence of the vector potential is 0, and scalar potential is 0. Don't confuse this with the Klein-Gordon field. And we have a vector potential, A x of t, which becomes an operator. This becomes an operator. Now, when you do the quantization, you know, of course, that the Hamiltonian of the electromagnetic field E squared plus B squared in the Coulomb gauge. This is just A dot squared. So this is an operator, A dot squared plus the curl of A squared. If you decompose the electromagnetic field into plane waves, sum of a k, let me not even bother, we're going to go through this. Decompose into sum of plane waves, it's just like the Klein-Gordon field, except there's a little twist that this is, because this is a vector and not a scalar, there's a slight difference, which is the following. A is a vector, so what this means is that in addition to k, the modes are also labeled. Some people will say I can't spell labeled, depends on what side of the Atlantic you're on, are also labeled by a polarization index. Polarization index R, which can be 1 or 2. This is an extra index, comes from the fact that while A is a 3-vector field, but because of its divergence free, when you decompose into plane waves, in effect you've got just maybe 2 extra vector degrees of freedom. Well, we'll come and do this, but basically there is you need a the modes are labeled, in addition to the wave vector, we've got a polarization index. And the end result, and we're going to derive this next week, so if you find it a little bit, hang on, you're not quite convinced, don't worry, I'll show you. The end result is that each mode Each mode is now labeled by K and R. The wave vector and R can be 1 or 2. Each mode KR has a simple harmonic oscillator Hamiltonian KR, which is H bar omega A at dagger KR A hat KR. These quantities A and A dagger, there's now one for each mode, where each mode is labeled by K and an index R, plus a half, where now these quantities, so there's a raising and lowering operator for each mode. Each mode is labeled by K and R, and what is omega? Here, omega is just the modulus of K. So this is as before, but with M is 0. So that you may remember that for the Klein-Gordon field, omega is the root of mod K squared plus M squared. Here, in effect, M is 0. People will often say that the electromagnetic field is a massless field. And of course, this is just some heuristic jargon. You know that the electromagnetic field carries energy, therefore it carries mass. So, this is just nonsense. Whether people say it's a massless field, what they mean is that in the mode decomposition, if you look at the relation between frequency and wave number, it's this rather than this. Okay, so there's this heuristic terminology, it's a massless field. Anyway, so what we have is we now have the same thing. We've got an infinite set of modes. We have except now the modes are labeled by wave vectors and polarization indices. Going on and on. Okay, this is the electromagnetic field. Mathematically, it's a sum of independent simple harmonic oscillators, one for each mode with this Hamiltonian, and the frequency is just the magnitude of the wave vector. And again, of course, the energy level. The energy levels of the KR mode are given by H bar omega NKR plus a half, where NKR is 0, 1, 2, and so on. So it's all the same kind of thing. So now the ground state. So that's the electromagnetic field. Let's just quickly go over a few cases. So the ground state. The ground state, what is often called the vacuum. Now there's a funny thing here that the vacuum used to be the term that we would use for empty space. The word vacuum is often used in quantum field theory to denote the ground state. When they say vacuum, it's just a word for historical reasons has been taken over from previous usage. Basically, what people used to think was empty space. I'd say I get an air pump, I remove all the air, take out all the anything that we can see, detect. What's left is supposed to be empty space. And according to quantum field theory, actually there are fields present in the vacuum that are in the ground state. they're in the ground state. That doesn't mean there's nothing there. Though, you know, people can argue about this. But let us say the ground states are all of the modes. All of the modes are in the lowest state. And each mode, of course, has an energy a half h bar omega. And the energy, so this vacuum is often denoted like this. So it's usually just written like that. And of course, what this really is a tensor product of an infinite number of ground states, one for each mode. Okay, so if you wanted to be fancy, I could write this as a product over K and R of the ground state for the Kth mode. Okay, is what it really is, but nobody bothers to write that. It's understood that that's what we're talking about. You just write this. This, what is the energy? The energy, let's write it like this. What is the eigenvalue? The energy eigenvalue is, as we saw for the Klein-Gordon field, it's the sum over the ground state energies for each mode. But now we have a sum over K and R. And we'll show explicitly later when we do this, but it's straightforward to show this actually diverges. The energy of the vacuum is actually infinite. Now, what you can do is a common trick that I mentioned for the Klein-Gordon case is if you convert this sum into an integral with respect to omega, and this omega goes from 0 to infinity, and it diverges. Let us say, a common line of thinking is to say that, well, actually, there's some maximum frequency beyond which the modes maybe don't exist, or somehow this description breaks down. Some people think that, so for instance, a very large frequency, roughly speaking, corresponds to a very short distance, is what corresponds to a very short wavelength. And some people think that space is not continuous all the way down, that if you reach a small enough scale, maybe the Planck scale, there's some minimum length. And so it wouldn't make sense to have a wavelength smaller than that. So they're inclined to say there must be really physically, when you do the mode decomposition of the electromagnetic field, you can't go below a certain wavelength. So there's some maximum frequency here, and this is actually finite. And there is a problem that if you sort of guess at what the maximum frequency might be, you know, the numbers that come out, this tends to be huge. You know, you expect to have a huge density of the vacuum. But still, some people think, you may have heard of something called dark energy. So dark energy is, according to our current understanding of the expansion of the universe, there's a large component of energy. Something like 70% of the energy content of the universe is something that we don't really know what it is. But one way of thinking about it is in terms of something like a vacuum energy. Some people think that it is actually a vacuum energy that is finite but large. But anyway, in for the kind of physics we're going to be talking about, never mind about dark energy, you can think of this as, I mean, there probably is, in effect, some sort of cutoff. There's some effective physics at short distances that makes this finite. But what we normally do is we don't worry about this, is we just say we're going to rescale our energy. We're going to say, here is energy. We're going to take this value, E0, to to be the origin. If you like, we're going to shift the energy by a constant, E0, so that we're going to measure all energies relative to the vacuum. Now, this is a cheap trick, as I've mentioned. You might think, well, you know, arguably in Newtonian physics, you might say, well, the origin of the energy is the origin in the sense of the mathematical origin is arbitrary. Why not? I could add a constant to the energy or subtract a constant. Doesn't make any difference. But in non-Newtonian physics, in modern physics, it does matter because energy is equivalent to mass, which is a source of gravitation. So, you know, energy does gravitate. In general relativity, energy you know, is a source of gravitation. So you can't just shift the origin of energy. So this is it's a bad argument. Okay, it's a bad argument. But this is what we do. We're going to measure relative to the vacuum. Okay. So now let's look at well, just briefly. The rest is the same as in the Klein-Gordon case. If I have this sort of thing with one mode excited and the others in the ground state, I have energy h bar omega relative to the vacuum. I have momentum h bar k, and this is interpreted, of course, here I have, this is a mode, let's label it Kr, the mode Kr. This is heuristically interpreted as the presence of a single photon. Okay, a single particle, which in the electromagnetic case, historically, these particles are called photons. It's a single photon of energy h bar omega and momentum h bar k, and something we'll discuss probably later, and polarization R. The photon has two polarization states, so R is 1 or 2. So there's a single photon in quantum field theory is an excitation of a particular field mode. I could have, if the mode was excited, was in the second excited state, what do I have? I have two photons of energy h bar omega and momentum h bar k and polarization R. I have two photons. What if I have, again, it's all just the same as in the Klein-Gordon. What if I have two different modes excited? Here's the mode Kr. Here's the mode K prime R prime. These are both excited. All the rest are in the ground state. Here I have two photons with energies h bar omega primed, and momenta h bar k prime, and polarizations R and R prime. Okay? So this is what you would call a two photon state with two different energies and two different momenta. All right. So now, so far I've just talked about the electromagnetic field in isolation. Now I'm going to talk a bit about what happens if the electromagnetic field interacts with other things, in particular an atom. Before I go on to that, just are there any questions about this? Any questions about this? So this will all be derived properly starting next Tuesday, but just when we go through the derivations, it helps a lot to have this picture in the background of actually what the end result is and what interpretation is. This is why I'm doing it this first. Okay, so let me now do the following. Let's consider an atom, a single atom, let's say a hydrogen atom, and we're going to treat the atom using your usual low energy quantum mechanics that you've studied. So you have, for instance, an excited atom, in the vacuum. An excited atom in the vacuum. So the atom, let's say at T is 0, the atom, let's just think about two energy levels. The atom has a ground state, it has a first excited state, and let's say the atom is in the first excited state. First excited state. Now, you know, or you should know, and we find experimentally that if I take an atom and I put it in the first excited state, and I have it in the vacuum, I have it as isolated, completely isolated, or as isolated as we can make it, is in the vacuum, that the atom will quickly radiate, it will drop into the ground state and emit what they say emit a photon. It will drop into the ground state. Now how does that happen? An atom is in the ground state. You might say, hang on, if I have my usual Schrödinger equation, and let me just write that the Hamiltonian is just the Hamiltonian for the atom, usual Hamiltonian for the atom, and psi at time 0 is an energy eigenstate. And so H hat atom acting on psi 0 is E1 psi 0. Okay, we have an energy eigenstate for the atom, and you might say that the state at time t is then going to be just the state, the energy eigenstate, times a phase factor. So I've got h bar as 1 here. Okay, it's just the phase factor. It's a stationary state. It will stay excited forever, in complete contradiction with what you see in the lab. So everything you learned is wrong. How does the atom make a transition down to the ground state? If it was truly isolated, it would just stay like this. This is if you just, your low energy quantum mechanics that you studied, in fact any quantum mechanics, if I have an isolated system, a truly isolated system in an energy eigenstate, it just stays there forever. Okay. Now, so how does this radiate? Well, what really happens is that it's interacting with the electromagnetic field. In fact, I'll tell you what we're going to do. Show you my masterly pedagogical skills, is it is interacting with the electromagnetic field over here. And a common interaction Hamiltonian interaction with the electromagnetic field common interaction Hamiltonian that we'll study a bit later on, is that you take the dipole moment operator, the dipole moment of the atom, and I mean this is only an approximation, but it is a good approximation. You take the dot product with the electric field operator. This is the electric field operator, the quantized electromagnetic field. What happens now is that, well, the Hamiltonian is actually the Hamiltonian of the atom plus this interaction Hamiltonian. So this is wrong. This deduction here, this implies this here. This is actually wrong. And what we're going to do later on is we'll study, or we'll treat it as a perturbation. In fact, the total Hamiltonian is the Hamiltonian of the atom plus the perturbation plus, of course, the Hamiltonian of the electromagnetic field. And normally you would write this. You'd write this the other way around. You would say the total Hamiltonian, Hamiltonian of the atom, the Hamiltonian of the electromagnetic field, plus the perturbation, the perturbative interaction. Now, what happens is, what is the effect of this perturbation? Just maybe draw it here like this. All right, let us say that at t is 0, I have the total state of the system. At t is 0, my total state is equal to E1 for the atom, okay, crossed with the ground state. Let's assume that the electromagnetic field is in the ground state. So I have an excited atom, T is 0, I have an excited atom, and the electromagnetic field is all in the ground state, all the vacuum. So the initial quantum state is actually of this form. I have a product state, excited state for the atom, ground state for the electromagnetic field. I now switch on this perturbation and calculate what happens. What you find is that over time, this evolves into the following. The atom can make a transition down to its ground state. And the electromagnetic field, for the electromagnetic field, one of the modes becomes excited. So one of the modes makes an upwards transition to here, so the atom falls into the ground state. So this is a mode, let's say this is KR, K prime, R prime, K double prime, all of these different modes. Over time, so the atom has dropped into the ground state, and one of the modes of the electromagnetic field has become excited, and which this occurs for appropriate K prime such that when you go through the perturbation theory, you find that the transition, the probability can be non-zero only if it respects, only if the transition respects energy conservation. So we need the following. H bar omega prime is E1 minus E0. Energy conservation. Okay, the atom has lost its energy, and one of the modes of the electromagnetic field has gained that energy. And of course, it has to be a mode such that the spacing, okay, this spacing between the ground state and the first excited state has to match the energy difference here. Okay, it couldn't just be any mode. It has to be in a mode such that that energy difference fits in this space here, according to this relation. So this is what has happened. Is that so? What really happens here is that the state. So I should maybe tell you that we're going to look at something called the interaction picture. We're going to calculate this in the interaction picture, where the state evolves via the interaction part of the Hamiltonian only. Now, you probably already met the interaction picture, but in any case, we'll be using it later. The operators evolve via the free part only. So what happens if I have a system where I have, Hamiltonian of the atom, the Hamiltonian electromagnetic field, and a small interaction? Is what we do, basically we have the operators in the Heisenberg picture, but with just this Hamiltonian. The remaining part of the Hamiltonian is used to generate a time evolution of the quantum state. So it's something that's a bit intermediate between the Heisenberg and Schrödinger pictures. But in any case, if you do this calculation, we'll show you that the term, the interaction term, causes the state psi to evolve from, so we had E1 across the vacuum, this evolves into the ground state for the atom, and an excited state of one mode for the electromagnetic field. And heuristically, you will say the atom has emitted a photon. We say the atom has emitted a photon. Now, this is heuristic language. It makes it sound as if there was something inside the atom. There was this little particle called a photon that's inside the atom and that it came out. That is all nonsense. What has happened is that the atom has excited an electromagnetic field mode. That's really what has happened according to quantum field theory. There is no photon. Photon is just a heuristic term. One of the modes of the electromagnetic field has become excited by the atom. This process could go the other way. I could have a situation where I have one of the modes of the electromagnetic field is excited. In other words, there's a photon present, and the atom is in the ground state. These two interact, and it goes back the other way. The atom becomes excited, and this mode drops into the ground state. What would we say? We would say, well, the atom has absorbed the photon. Okay, what has it really done? It's absorbed energy from one of the modes of the electromagnetic field. Okay. I'm now going to sketch for you, there we go, good, we've got time. I'm going to give you a little sketch of how all this generalizes to electrons and positrons. Before we do that, any little questions here?
The atom itself is charged and is capable of having an electromagnetic field. So when you're writing Hamiltonian, separating the H atom, H electromagnetic field, does that mean that the electromagnetic field is an external electromagnetic field, or can it also be that the atom is interacting with its own field?
right? So in this approximation, the short answer is that you would say that it's interacting with the electromagnetic field in the rest of space. That's really what's happening. Strictly speaking, to do this properly, I would have to consider the atom as made out of electrons and you know, the various particles, and strictly speaking, the electromagnetic field of the atom itself is quantized and so on. But there's an approximation where you treat that part of the field classically, and we'll look into this a bit later on. But this is, you know, this thing with this dipole interaction. It is just an approximation, but the short answer is that if you imagine, let's put it this way: if you say mathematically the following situation: I have a free electromagnetic field, and I have another system which has some energy levels, and I couple the system to the electromagnetic field in this way, then you get these kinds of transitions. This model is a good model of how atoms make transitions, but the actual the derivation of this approximation from the underlying theory, where you treat the atom properly according to quantum field theory, is a bit complicated. And any other questions? Okay, all right. So let me now tell you. I've told you that a photon is really an excitation of an electromagnetic field mode. So, a photon is really an excitation of a mode of the electromagnetic field. Similarly, an electron is really an excitation of the Dirac field. So what's going to happen is that later on the Dirac field, which is a four-component complex field, becomes an operator that we expand as a sum of plane waves. And just conventionally, while the modes are labeled K for the electromagnetic case, for what are called massive fields, they're labeled with P. Or sorry, for Fermi, fields for the Dirac field is just labeled P rather than K. So what we have are an infinite number of modes. If you expand the Dirac field in plane waves, you get an infinite number of modes, just like for the Klein-Gordon and the electromagnetic field, but where each mode is labeled by, instead of a wave vector, it's the same thing, it's just a convention. I mean, h bar is 1, p is h bar k, h bar is 1, p is equal to k. It's just a convention. You use k when you're talking about Klein-Gordon or the electromagnetic field, and you use p. It's just a notational convention. It's the same thing. Each mode is labeled by a wave vector or a momentum vector. In addition, remember in the electromagnetic field we have a polarization index. Here you have a spin index. S is a spin index, which you could write as S is plus or minus. S is plus or minus. We'll define it properly later, but it turns out that there's because this is a multi-component field, as well as to have a complete set of states in this expansion, as well as the this 3-vector momentum, you also need a spin index. And there's one twist. There's one twist. That the fields anti-commute. I've said to you that it's just applying standard quantum mechanics to a field. There's one slight oddity, that when you're looking at fermion fields, such as the Dirac field, the field anti-commute, and when you look at the expansion, and you find, just as usual, you will find these raising and lowering operators. There are raising and lowering operators for each mode. And you might think, okay, I'm going to get this. I have again, simple harmonic oscillators. The Hamiltonian is like for each mode is like a simple harmonic oscillator, and of course here the mass is not zero, so it's a bit like the Klein-Gordon field. The mass is not zero. But the fields anti-commute, and this commutation relation, this commutator is replaced by an anti-commutator. Where the anti-commutator, let me just write it here, A, B, in case you've not seen it, the anti-commutator is defined as AB plus BA. It's AB plus BA. And because of this difference, because this is an anti-commutator, you still get a set of discrete energy levels, except there's nothing up here. For each mode, there are only two possible energies. In other words, what you find is that the energy is h bar omega NPS plus a half, where NPS can equal 0 or 1 only. Each mode is either in the ground state or in the first excited state. I say first excited state, there are no other excited state. But what is this? This is just the Pauli exclusion principle. You cannot have two fermions in exactly the same quantum state. If I had, imagine if I had the second excitation, we would say, oh, I have two particles with this momentum and this spin. No, you can't have two particles with the same momentum, same. You can only have both one. Okay, so there are only two energy levels. So what happens is the twist in the Dirac field is that you have an infinite number of independent harmonic oscillators. Each mode is labeled by momentum and a spin, but each mode has only two energy levels, excited and unexcited. And that comes from, all the mathematics is the same as what we had for the electromagnetic field, except here you've got an anti-commutator, and that causes this difference, that there are no higher levels. So now, in 5 minutes, I'm going to show you something sexy. All right? So, it turns out that when you quantize the Dirac field, there are actually two types of modes. Two types of modes corresponding to positive and negative charge. We're going to look at the charge operator. We'll find something called the charge operator. We'll find that if you have that an electron is a state where all of the modes are in the ground state except one. This is an electron of momentum p, spin s, and charge minus e. There is another set of modes. Basically, there is a doubling. You have this infinite set of modes. Then there's another set of modes, because this is a 4-component field. And you have an extra set of modes that corresponds to oppositely charged particles. So you've got another copy of modes where if one of these modes is excited, this corresponds to a positron of momentum p, spin s, and charge plus e. So there's something called the charge operator. And when we look at these states, and we'll find that this state is an eigenstate of the charge operator with eigenvalue minus e. And this is and then there's another set of excitations where the eigenvalues of the charge operator have the opposite sign. And these correspond to what you normally call electrons and positrons. So, let me show you something. What can happen in quantum field theory is, let us say I have an interaction between the Dirac field and the electromagnetic field. And this is called, the theory that describes this is called quantum electrodynamics, or QED, which is going to be the culmination of this course. We're going to describe the interaction between these two different kinds of fields. And let me just take, in 5 minutes, show you the kind of thing that can happen. Imagine that at t is 0, I have, instead of drawing all the modes, let me just say I have an electron in the state ps. Okay, so what do I mean? I mean the electron-positron field, or the Dirac field, all the modes corresponding to negative charge are in the ground state except one. Okay, so I say, oh, there's an electron with momentum p. I also have one mode of the positron side of these modes excited. And let's call this P1 and S1. And here I have a positron with momentum P2 and spin S2. And let's say that the electromagnetic field is all the modes are in the ground state. So here I have, let me just draw two modes. You just draw two modes and let me call them. So a photon, so if you like, it's a photon mode labeled K1R1. It's a photon mode labeled K2R2. So the electromagnetic field is all in the ground state. Two modes of the Dirac field are excited. One corresponds to an electron of momentum P1, one to a positron of momentum P2. Let's not worry about the spin. Because these fields interact, energy can be exchanged between them. Over time, the following can happen. So here I have the mode P1S1, so let's call it the electron mode, the positron mode P2S2, I have a photon mode K1R1, a photon mode K2R2. What can happen is that these can drop into the ground state and these can become excited. And this can happen in perturbation theory. Of course, there are an infinite number of electromagnetic modes. Which ones can become excited? Well, the modes have to satisfy energy conservation and momentum conservation. All right. But now let's just see, well, hang on, what is the interpretation of what happened here? Is that at T is 0, we had one electron, one positron, and no photons. Okay, gamma is often used as shorthand for photon. There's one electron present, there's one positron present, and there are no photons present. Afterwards, later, there's no electron, there's no positron, and we have two photons. What has happened here, heuristically, you could represent this as the following diagram. If I have time running this way, I would say, well, I have an electron coming in and a positron coming in, and somehow they vanish, and out come two photons with energy, momentum, of course, conservation satisfied. This is called electron-positron annihilation. Electron-positron annihilation. And what we're going to do in this course is we are going to calculate the probabilities or the cross sections for such processes. Once you've defined for the electromagnetic and for the Dirac field these various possible eigenstates, you then let these fields interact, you can get transitions of this form. The transition could also take place the other way. I could start out with, there's no electron, no positron, I just have two photons. If they're sufficiently energetic, you can go this way, the photons disappear, and you create an electron-positron pair. So the reverse process is called pair creation. Obviously, the total energy of these photons has to equal at least 2mc squared, okay, in order for this to happen. But that can happen, pair creation. So this is how, the actual, what you might call the creation and destruction of matter, what you normally call matter. Electrons, positrons, massive charged particles, what you normally call matter. In quantum field theory, it can be created and destroyed. Here you have, two oppositely charged particles that, at least the heuristic terminology would say, you have two oppositely charged particles that annihilate to produce photons. Or the reverse can happen. You can have energetic photons that create an electron-positron pair. What is happening from the point of view of quantum field theory is that, well, I have different kinds of fields that have different kinds of excitations. If some of the modes are excited and others are not, if I let these two kinds of field interact, energy and momentum can be transferred from one mode to the other. These can become de-excited, others can become excited, and this corresponds to these processes of particle interaction and so on. In fact, maybe I may as well just say this too. If I had, say, electron-electron scattering in quantum field theory. Let us say I have an electron coming in with momentum, let's ignore the spin, let's just call it P1, oh, let's put in the spin. With momentum P1 and spin S1. And let's say I have another electron coming in with momentum P2 and spin S2. And these two electrons interact, and what you normally say, they scatter off each other. I have outgoing electrons, but with different momentum. Let's call it P1 prime, and maybe different spins. And let's ignore the spins, get it too messy. P1 and P2, P1 prime and P2 prime. You can describe this in perturbation theory, and of course you have conservation of momentum and of energy. How do you describe this process in quantum field theory? In quantum field theory, what is happening is the Dirac field. Let's just concentrate on these four modes with momentum P1, momentum P2, momentum P1 prime, momentum P2 prime. Initially, I have an electron of momentum P1, and an electron of momentum P2. There's no electron of momentum P1 and no of P1 prime and no electron of momentum P2 prime. This makes a transition to the following. If I have here, these are the same, sorry, this is a bit squashed, but these are the same four modes, P1, P2, P1 prime, P2 prime. These two become de-excited, and these two become excited. Okay? So what happens, what you normally think of as, oh, I have an electron, momentum P1, momentum P2, they scatter to produce an electron of P1 prime, P2 prime. What's happening in quantum field theory is that, well, the modes with these momenta were excited and these were not. Energy, momentum can move around from one mode to another, and you end up with the outgoing state. These two modes drop down into the ground state, and these become excited. And so afterwards, I have a state where I have an electron with this momentum and an electron with that momentum. So there's a sense in which the electrons with these momenta have disappeared, and the electrons with these momenta have been created. Okay, this is the actual account that takes place in quantum field theory. So we'll see how to calculate these processes. That's the end of the sketch. Next Tuesday, we're going to get down to business. We're going to quantize the electromagnetic field and show how, by the end of this course, you will be able to calculate electron-electron scattering at high energies. You'll be able to calculate electron-positron annihilation. These are all the exciting things that are coming your way. Okay, so any quick questions? Any quick questions about that? All right, I guess there are going to be more questions when we get down to the nitty-gritty and working it all out properly. All right, thank you.